We are on Unit 2, Notes 3, Derivatives of Logarithms. First of all, I'd like to just refresh your memory on logs a little bit. So we're going to talk about some of the properties of logs. Okay, so properties of logs. First of all, log base b of a is defined only when b, the base, is not 1. So the base cannot be 1, all right? And a is greater than 0 and b is greater than 0. So b has to be greater than 0 but not 1, and a has to be greater than 0. Okay? Number 2, log base b. If the argument, if a is 1, so if you have a 1 here, any base, this log would be 0. So if the argument is 1, the whole log is 0. Okay? Number 3, if your base is the same as your argument, so maybe log base 7 of 7, log base 5 of 5, log base e of e, those are all 1. Okay? Number 4. This is one we use quite often. Okay? What if your argument has an exponent on it? So it has to be like this. Okay? If your argument has an exponent on it, you can move the exponent to the front and make it the coefficient. Okay? We're going to find that that's very useful for us when we're doing derivatives. Okay, so that's a popular thing to do. We use this a lot too in our simplifying. We use those in our simplifying, but this is one we use to actually find a derivative. Makes things easier for us. Okay, another one we do similarly. It allows us to find a derivative more easily. What is the log of a product? M times n. Okay, well, this is the same as the log, same base, of m plus log base b of n. Okay, we're going to find that by this is expanding this log. Here's a log that's condensed. This is expanded. In the expanded log, it's easier to take the derivative than it is a product. Okay, so we use that one a lot. We also use the one with the quotient. So what if we have m divided by n here? Well, it's log base b of the top would be, whatever's on top is positive, whatever's on bottom will be negative. So minus log base b of n. And we use that one too for derivatives. Okay? All right. Let's see. Natural log x. Natural log of x means log base e of x. That's what that means. Okay? Natural log, ln. If no base is shown, like log of x like that, it's assumed that that base is 10. Okay? And here's this last one is called the change of base formula. This change of base formula, we can change the base and make it any other base we like. Log base c of a divided by log base c of b. That's how that works. Okay? What we do with this, because natural logs are so much easier to deal with, not so much easier, they're slightly easier to deal with than other bases. So we change this to ln. We make the base e. So ln of a over ln of b. So we'll be using this a little bit. Okay? And this is the change of base formula. All right. Let's review real quickly what the graph of natural log looks like. The graph of natural log. So we're going to say, or any log, but specifically natural log. For the graph of y is equal to ln of x, we know that when x is 1, the log is 0, right? So when x is 1, the graph goes through there. Okay, we also know that when x is the same as the base, y will be 1. So when x is e out here, we should be up at 1. So those are the only two things that I want to make sure I kind of get right on my graph. And then I draw a smooth curve. Okay? So that's a quick sketch. Quick sketch. All right. E, remember? E is equal to 2.718281828 keeps on going, not repeating, not ending. But it's just a number about 2.7. All right? So I drew it a little bit too close to this 1, didn't I? It should have been out a little bit more, but whatever, you get the idea. It's a quick sketch. All right. So a couple things about this graph. What is the limit as x goes to infinity of ln x? What's that limit? Well, as x goes to infinity, what is y going to? Is there some asymptote there? Is it getting closer to some number, or is it increasing without bound? Well, it is. It's increasing without bound. So this limit is infinity. So the limit does not exist, okay? So, yes, it does go to infinity. It just goes there very, very slowly. Very slowly. Let me grab my calculator real quick. Let me show you how slowly it goes there. So when x is like, let's say 10, what is y? 2.3. What about when x is 100? Well, we're all the way up to 4.5. What about ln of 100,000? ln of x is way out at 100,000. How far up are we? Well, we got up to 11.5. Okay, so yes, it's going to infinity. It's just going there really, really slowly. Okay, so keep that in mind. All right, we'll do more with that later. Fun stuff later. Okay, another couple things about this graph. So we did the limit. Y is equal to ln of x is the following. So first of all, it is continuous for all x. For all x. There are no jumps, no breaks, no holes. It's continuous. It is increasing for all x. No matter what x is, when you go to the right, for if as x increases, y increases as well. Y is always going up. So that means x is increasing. I'm sorry, the function is increasing. Okay? Number 3, this graph is concave down for all x. We're going to talk more about that next unit, I believe. But concave down is like a frown. That's going to be my little thing. So it's like a frown or part of a frown. Do you agree that this would be like part of a frown? If we were drawing a frown, it would look like that. Well, concave down is part. It has to be either all of it or part of it, but that's concave down. Okay? We'll talk more about that later. And lastly, this function is called 1-to-1. 1-to-1 means it passes the vertical line test. It only crosses, any vertical line crosses at most once, and it also passes the horizontal line test. Any horizontal line crosses the curve at most once. So that's called 1-to-1, all right? And that means that the inverse is also a function. So not only is ln x a function, but its inverse is also a function. Okay, it seemed like there was, another thing. Well, we've already talked about that. This function is only defined when x is positive. X cannot be 0. X is only positive. All right. Okay. Let's talk about derivatives. So derivatives. The derivative of logarithms. I'd like to start with the derivative of ln of x, okay? Derivative of ln of x. So I'd like to be able to write something. What is the derivative of ln x? Okay, that's what we're looking for. So I'd like to get out my calculator again and show you something here. So we have, let's see, I'm actually going to go to my graph, I think. I would like to know what the derivative of ln x is. Well, there is a derivative button on your calculator. It's very handy. We use it quite a bit. It's under math. So if you push math, and then it's number 8. So it's down here at number 8. You don't have to scroll all the way down there. You can just push the number 8. But let me show you where it is down here. There are more down here. Oops. Ah. So here they all are. So do you see how it says n deriv? That's the derivative. Another one that we use a lot is this function integration. So we use both of those a lot. When we do integrals, we'll be using math 9, I call it a lot. So math 8 will give you the derivative button. Okay, and you see it's even our same notation. So it's flashing here. We need to fill that in. I'm going to put an x there. Okay, and here I'm going to put our function ln x. Okay, close my parentheses. And then over here, if we're on the home screen, this always has to be a constant we put in. But on the graphing screen, if we just put x, that constant will change as our graph changes. As it's plotting points, the x value will change. So this will give us the graph of the derivative of ln x. Okay? So this will, again, when I hit the graph, we'll get the derivative of ln x, not the graph of ln x. We already know what that looks like. All right, I'm going to do zoom forward just to get a nice 1-to-1 ratio graph. Okay, so it makes sense that the derivative is only defined for positive x values, right? Because ln x is only defined for positive x values. So I'm not shocked that, wait, it's only over here. Well, I'm going to trace this. Let's trace this. So again, when x is 0, we don't have any y. So I'm going to go to the right. Okay, when x is 1/10, y is 10. When x is 1/5, y is 5. When x is 3/10, which is close to a third, but not quite. Anyway, this is 3 1/3. 0.4, so 4/10 would be 2. So anyway, 1/2 and 2. What is the relationship here? 1, 1. This is given a little error. Don't let that bother you. The calculator always uses a numerical method to evaluate these derivatives. So oftentimes you'll see a little error. You have to interpret it correctly. Okay. So what is the relationship? We had 1/2 and 2. We had 1/5 and 5. Okay. We had 1 and 1. Okay. If I keep on going to 2, let's see when x is 2, y is 1/2. So what graph is this? That is the graph of y equals 1 over x. And I can show you that by coming down here. I don't have one of the, I wish I had a colored graphing calculator where it graphed in different colors, but I don't. I've had this for a little while. So if I graph 1 over x over that, you'll see, well, there's that part of it. But look, it lined up very nicely. And if I trace over here again, so that point is on the derivative, and if I go down to the other one, you can see it didn't change. I'm looking at the y value, and look at the y value does not change. Well, the very end of it changes because that's just the little error in the derivative. Okay, so the derivative of ln x is 1 over x. Love it. Okay. This is something to know. I like to star the things you need to know. Box and star. Okay. Now, what if we have the derivative of ln of some other letter, like u? What if we have that? What's the derivative with respect to x? Well, this is just a little implicit differentiation, really. It would be 1 over u du dx, right? Little chain rule or implicit differentiation. Okay. Another way to write this would be u prime times 1 over u, so u prime over u. Okay. Now, what about, I would like to know what is the derivative of another base. So what if we have log base b of, should we do u or should we do x? Let's just do u. Let's do that. Okay. All right. We'd like to know what that is. What is that? Okay. Let's come over here. Log base b of u. I'm going to change it because I know what the derivative of ln is. So let's change this to ln's. So this would be ln of u over ln of b, right? Change of base formula. Back from our properties at the beginning of today's lesson. Okay? ln of b is just a constant, because b is just a constant. The base will always be a constant for us guys. So ln of b is just a constant. Okay? So that's something we can just pull out. 1 over ln of b, right? So log base b of u is 1 over ln of b times ln of u. This is just a constant, like a 5 or a 10 or whatever. So the derivative with respect to x of log base b of u will be the derivative with respect to x of 1 over ln b times ln u, where 1 over ln b is just a constant. So it's 1 over ln b times the derivative of ln u. 1 over u du dx, or u prime over u. Okay, so how I remember this, I begin, if it's not ln, I know I need to fix it. I need to make it 1 over ln of whatever the base is. And then u prime over u. That's how I remember it. Okay? So yeah, know all of these. Alright, time for some examples. Example 1, and we're going to be finding the derivative in each of these. So the directions would say to find the derivative. F of x is equal to natural log of 3x squared plus 4x minus 1. So the derivative would be, okay, it's natural log, so it's 1 over u times u prime, or u prime over u. So the derivative of this divided by that left alone. That's it. Notice, you guys, that the derivative does not have a natural log left in it, okay? The derivative does not have a natural log here, okay? No natural log. This has a natural log because it still has that b. Okay? That's just a constant though. Okay. Number 2. G of x is equal to the natural log of the cube root of x cubed minus 3x. Okay, well here we have a choice. And we're looking for g prime. Here we have a choice. We can go ahead and take the derivative of this. If we do, we'll need the chain rule because this is x cubed minus 3x raised to the 1/3 power, right? We can do that, or we can use our log properties. Our log properties, specifically this guy. If we have the cube root of x cubed minus 3x, that's going to equal x cubed minus 3x to the 1/3, right? I forgot my ln. We have ln here. So that 1/3 we can pull out front. Whoops. We can pull that out front. And then we just have 1/3 times the derivative of that natural log. And we don't need to use a chain rule on that. So simplify first. Simplify first. So this will be 1/3 ln x cubed minus 3x. Okay? So the derivative will be 1/3 times the derivative of ln of x cubed minus 3x. So derivative, that's your u prime. It's also like the chain rule, over x cubed minus 3x. This would be safe stop, but I see that 1/3 and all these 3's on top, so as a multiple choice answer, it would look like this. Okay? So you guys always simplify. And when I say simplify, I really mean expand. Expand. Get your logs as spread out as you can do it. So get them all spread out, and then take the derivative. Okay? Number 3. We have h of x is equal to natural log of 2x over x plus 3. Okay? Now this is a quotient, so if you just do u prime over u from here, you'll need to use the quotient rule, which is fine, you can totally do that. But my suggestion is to spread this out, expand it. So this is natural log of the top minus natural log of the bottom. And then I look at my arguments. Can I take the derivative of each of these easily? Yes, I sure can. We could spread this out into ln2 plus ln x. We could. but I can take the derivative of 2x pretty easily, so I think I'm just going to do that. So h prime is equal to the derivative of ln of 2x is 2 over 2x. The 2's will cancel, and we'll just have 1 over x, right? Minus the derivative of ln of x plus 3. The derivative of x plus 3 is 1, and then we put it over the x plus 3. Say stop. A multiple choice answer might be this, or they might get a common denominator. The common denominator would be x times x plus 3. We would need to multiply this fraction by x plus 3 over x plus 3. This fraction by x over x. So this would be 3 over x times x plus 3. So this might be the multiple choice answer, or this might be the multiple choice answer. This one would not be the multiple choice answer because of the 2's there. Okay? All right, number 4. Y is equal to the natural log of the absolute value of cosecant x. Why absolute value? The absolute values just ensures that the argument is positive. Okay, it just ensures it. So I will say this, in these other ones we've done, we didn't have absolute values here, right? And there are x values that would make that argument negative, but we didn't say anything about that. We could have said that, or it could have been given to us like that. It just wasn't. But when it's given to you like this, and you're finding the derivative, you really don't have to worry about the absolute values. They are there only to ensure that your argument is positive. So let's go ahead and find the derivative. I'm going to call it dy dx. I need the derivative of the argument. The derivative of cosecant is negative cosecant x cotangent x, all divided by the plane u, or the inside. Safe stop. Not multiple choice, because you can reduce that. And that would be it. That would be your multiple choice answer. Okay? Number 5. F of x is equal to log base 7 of 3x to the 5th. Log base 7 of 3x to the 5th. This log base 7, in my mind, I'm thinking of, oh, this was one where we had to use that change of base formula, right? Change of base formula, and I'm going to change it to natural logs, okay? So that's still just f of x. So f prime of x, this 1 over ln x, I'm going to pull out to the front. I'm sorry, ln of 7. The 1 over ln of 7 I'm pulling out to the front. And then I'm just multiplying by the derivative of ln of 3x to the 5th. And that would be 15x to the 4th over 3x to the 5th. That's it. Safe stop. Not multiple choice, because you can reduce that x expression in the back. This would be 5 over x ln 7. That would be the multiple choice answer. Okay? Number 6. G of x is 3x log base 5 of x squared plus 7. When I see log base 5, I think, oh, I need to change that to natural logs. So I'm going to have that ln of 5. I'm going to pull that out to the front. In fact, since there's already a 3 out here, I'm going to make that 3 over ln 5. And then I'll have x ln x squared plus 7. I like this because it's just one constant here. So I just will multiply that by my derivative. So g prime is 3 over ln of 5 times the derivative of this. So for the derivative of this, I need the product rule, right? Product rule. So 1 times ln x squared plus 7 plus x times the derivative of this is 2x over x squared plus 7. And they would clean that up slightly, but not too much. They would pull that maybe 2x squared up there. That's all they would do. Okay. Okay, number 7. We have h of x is equal to log base 2 of x over x squared. Well, as soon as I see that log base 2, I think, oh, let's change it to ln. Okay? So I'm going to have 1 over ln of 2 times ln x over x squared. I take this out because it's just a constant, like a 5 or a 10 or 3 or whatever. So now we're taking the derivative, and I've got that constant I'm pulling out. And now I take the derivative of what's left. I need to use the quotient rule here. So start up on top, take the derivative. Derivative of ln x is 1 over x. Multiply it by the denominator, x squared, minus, now the derivative of the denominator is 2x, times the top left alone, all over the denominator squared, so x to the 4th. This would be safe stop, but not multiple choice. X squared times 1 over x is x, right? So 1 over ln 2 x minus 2x ln x over x to the 4th. There's an x in every term, and if there's an x in every term, you can factor it out and then reduce it. So this will be 1 over ln 2 times 1 minus 2 ln x over x cubed. This would be the multiple choice answer, or it could be a multiple choice answer. Sometimes they will rewrite this with the log base 2 again, but I kind of like this method here. All right, number 8, last one. Find dy dx if natural log of xy plus 5x is equal to 50. Okay, let's not forget about implicit differentiation. Okay, so we're going to take the derivative of both sides with respect to x, right? d dx, derivative both sides with respect to x. All right, in this first one, well, I want to split this up, right? This is ln of x plus ln of y, right? That's ln x plus ln y. So the derivative with respect to x, the easiest way to do this is not using the product. I could use the product rule, but the easiest way to do it is just to write this as 1 over x plus the derivative of ln y with respect to x will be 1 over y dy dx, right? Plus the derivative of 5x with respect to x is 5. The derivative of 50 with respect to x is 0. And now just solve this for dy dx. So dy dx, 1 over y dy dx will be negative 5 minus 1 over x. Multiply both sides by y. Okay, that would be a safe spot. What else could they do for that? we could get a common denominator and stuff. Anyway, they might pull out a negative. They could do some other things with it. They could write this as negative 5y minus y over x. You could get a common denominator. It depends on what their multiple choice answers are. If this is not one of the answers, then I do something with it until I get it to be one of the answers that are in the list. If they wanted a common denominator, it would be 5xy minus y all over negative 5xy minus y all over x. Here they would definitely pull out a negative. Okay, when you pull out a negative, it would look like that. Okay, so one of those would be the multiple choice answer. All right, so that is derivatives of natural logs.